Again, to do that, we need to define the canonical variables. And in our case, I think I'm gonna take eta and rho g eta dot, which I'm gonna call it. So this is I'm gonna call this p equal eta. Sorry, this is q equal eta, and this is gonna be p. Or maybe no, let's leave it eta. Okay. So this is the momentum density. Because now we have a system that is distributed in space, and as a Hamiltonian, H, which will depend upon eta and P, let's take the total kinetic energy, P and Q. Now is with the sum. This is equal to integral between 0 and L of 1/2 rho g eta dot square plus 1/2 alpha eta square plus 1/2 capital T eta x square in delta x. But now I can rewrite this as p square divided to rho g. Okay, and as you can see, we have defined what is the Hamiltonian now. What is the Hamiltonian? But let's see if it's a good Hamiltonian. You know, so we have to. If it's a good Hamiltonian, this energy should be conserved. So the Hamiltonian, which depend upon eta and p, it's going to be equal. Let's call the rho g equal gamma, the specific weight per unit length. And we have this new formulation 0 to L of p square over 2 gamma plus 1/2 eta square plus 1/2 t eta x square in delta x. Okay, so if this is a good, let's see if this is the Hamiltonian. So if this is the Hamiltonian, let's derive let's consider an observable f, which depend upon, in general can depend upon eta and p and time. And in theory, we can even include this partial derivatives. But for now, let's keep it simple. Now, let's consider an observable of this type, which is going to be given by the integral between 0 and L of a function of eta, p, and t in delta x. So this is the total observable, and here we have the observable density, because we need always to have something that is distributed in space. And let's compute what is the total derivative of this function. And of course, to do that now, this is equal to what? Is equal to the integral between 0 and L of open parentheses partial of f with respect to time plus partial of f with respect to eta times d eta dt plus df dp times dp dt in delta x. But I need to know what are these time derivatives. but this time derivatives, they come from the Hamiltonian formulation, because now we know what is the Hamiltonian. Is right, Hamiltonian depend upon eta and p, and we know that if the Hamiltonian that we chose is a good one, we know that the PDT has to be equal to minus the partial variational derivative of the Hamiltonian with respect to Q, and then partial of eta with respect to time equal to plus partial of eta, variational derivative of eta with respect to p. And what was the Hamiltonian in our case? The Hamiltonian was given by the interval between 0 and L of what? Of 1/2 p squared divided by gamma plus 1/2 alpha eta squared plus 1/2 t eta x squared in delta x. Now these partial derivatives these variational derivatives are easy to do, because this is equal to minus open parenthesis. The partial with respect to Q is going to be equal to, let's call this quantity the Hamiltonian density. Partial derivative of the Hamiltonian density with respect to Q minus partial with respect to x of the partial of h with respect to q dot. But in our case, you see that oh, sorry, here the q is eta. Yeah. So you see that this term is there. Instead, here, now, when we do the partial with respect to the variational derivative with respect to p, the only dependence appears here in the kinetic part, and so we simply have plus the total derivative of h, the partial derivative of h tilde with respect to p. And this is equal to what? This is simply equal to p divided by gamma. And here what we get? Here we get minus, let me do it. Here we get what? We get minus open parenthesis the partial of h with respect to eta is equal to alpha eta, and then we have minus the partial with respect to x of what? Of the derivative of h with respect to eta x, which is basically t eta x. Okay, so, and as you can see now, this result is simply equal to minus alpha eta plus t eta xx. And you see that, you know, we basically recovered the PDT equal minus alpha eta plus t eta xx, and d eta dt equal p over gamma. And it is pretty easy to see that this is basically the definition of the momentum, and this is the original equation that we derive, is the wave elastic equation. Okay, so this is the correct this is the Hamiltonian formulation of our original equation, because remember that p was exactly given by rho g eta dot. That's how we define it, and it comes naturally from this Hamiltonian formulation. And then you can see that here the elastic equation naturally follow. Okay, so we basically prove, I should have done it before, sorry, before doing the observable, but this Hamiltonian formulation that we define with this Hamiltonian density, if he define a well-defined Hamiltonian system. Okay, so we recover from this Hamiltonian formulation, we recover the original equations. But now we need to show that we get good Poisson brackets. That's the key, basically. Okay, and that's what I was doing here. Now we need to derive the let's consider the time evolution of a generic observable, and again, so we add this f given by the interval between 0 and L of f, which is a function of eta p in generally time. So let's do it again. So we have the total derivative with respect to time is equal to the interval between 0 and L of what? Of df with respect to time, which is fine, plus df partial of f with respect to eta d eta dt, plus df dp times partial of p with respect to time times delta x. And then, I show you now that what? I show you that d eta dt is equal to plus the variational derivative of h with respect to p, and the partial of p with respect to time is equal to minus the partial variational derivative of h with respect to eta. Okay, we just prove it. Now, this I can write it as equal to the variational derivative of capital F with respect to eta, okay, times partial of h with respect to p, plus df dp small f. Okay, this is kind of still like a density. Okay, I can write it as a variational derivative of f with respect to p times, open parenthesis, minus variational derivative of h with respect to eta. So it looks like I can rewrite, the total derivative of this observable is equal to the integral between 0 and L partial of small f in dx plus integral between 0 and L, open parenthesis, variational derivative of f with respect to eta times variational derivative of h with respect to p minus variational derivative of f with respect to p times partial of h with respect to eta in delta x. But since the length is fixed, I can bring this derivative outside, and so this is equal to partial with respect to t of the integral between 0 and f in delta t. But this is equal to derivative of f with respect to time plus this integral. Okay, so let's see again what we found here. We started with a generic observable between 0 and L of f eta p t delta x, and then we were able to rewrite the total derivative df dt as the partial of f with respect to time plus this integral between 0 and L. And now here I define a bracket given by f comma h in delta x, and this bracket f comma h is given by partial of f with respect to eta times variational derivative of h with respect to p minus partial of f variational derivative with respect to p times variational derivative of h with respect to eta. Okay, so this is a commutator between f and h, and then this commutator allow me to define the Poisson bracket and this is my Poisson bracket, and which is given by fh integral between 0 and L of f comma h in delta x. Okay, so this is a good Poisson bracket because it satisfies the properties that f a comma b equal minus b comma a, and then this implies that a comma a is equal to 0, and then we have the famous Jacoby identity, which is also satisfied. Okay, a comma b c plus c comma a b plus b comma c a is equal to 0. Okay, so this is the most important property that has to be satisfied, and of course this is related with the group properties of the Lie group associated to the Hamiltonian dynamics, but that is this is you know, very well advanced, so I'm not gonna explore it. So it requires some deep knowledge of algebra. This actually is enough, so at least we are operational and we can compute, we can do computations with this by, you know, mastering this framework, the Hamiltonian framework. So the important things to notice here, since now we are dealing with distributed systems, you can see that the Poisson bracket is given as a functional which depend on variational on a commutator of given in terms of variational derivatives. So there is an increased level of you know, difficulties because we have to deal with functionals instead of function, but more or less, you know, things are, you know, they are doable. Okay, as long as, you know, we master calculus of variations, you know, we can compute all these properties. What is nice is that now, given this formulation, so knowing the evolution of any observable f in terms of a Poisson bracket, here we have the extrinsic dynamics, extrinsic time dependence, and intrinsic time dependence induced by the dynamics. We can derive any evolution. Okay, so what does it mean? From this formulation I can rederive my original equations, is right? Let's see if it's true. So so we have these results equal partial derivative with respect to time plus this the Poisson brackets, and the Poisson bracket a comma b is given by this functional, in which there is the appearance of the commutator between a and b, and the commutator between a and b involves the variational derivative of a with respect to eta times the variational derivative of b with respect to p minus partial of a with respect to p times partial of b with respect to eta. Okay, what I would like to do now is to rederive the Hamiltonian equation from this generic formulation of an observable, but I need to pick the right observable. Okay, let's assume I want to derive the evolution for eta. So I pick then as an observable f equal integral between 0 and L of eta of x prime t delta x minus x prime in dx prime. Okay, and And for example, now let's do this total. Let's apply this formula, and of course, now the total df dt is gonna be equal to what? There is no extrinsic dependence on time on this functional, okay? So this derivative disappear, but I have this df dt in my case, df dt for this case is equal to the integral between 0 and L of d eta dt at x prime t delta x minus x prime dx prime, which is equal, if we apply the localization property of the delta, of d eta dt applied at x. Okay? So I know already that this total derivative is going to be equal to this. Now let's compute the brackets. This total has to be equal to the brackets between f and h. But this is equal to what? This is equal to the integral between 0 and L of the bracket between f and h in dx. But this is equal to the integral between 0 and L partial of f with respect the variational derivative of f with respect to eta times variational derivative of h with respect to p minus variational derivative of h with respect to p times variational derivative of h with respect to eta in delta x. But now this is my functional, so this variational derivative df d eta is equal to what? Is equal to the integral between 0 and L of eta, of delta x minus x prime. Here we can do the integration in x prime times dh dp. Okay, minus, now the derivative here doesn't show up, there is no dependence of f on p, so we're done, because this is equal to what? Now I apply the localization property of the delta. This is going to be equal to partial variational derivative of h with respect to p computed at x. And so I have that this is equal to this, and this is the first Hamiltonian equation for the first Hamiltonian equation for eta dt. The same reasoning can be applied to, so what we get here? So we get the d eta dt equal plus partial of h with respect to p. Of course, I can also derive with the same reasoning the p dt equal minus partial of h with respect to eta, and which observable should I take? What about this? Because we are done with this. The observable for the dynamics of p, it is going to be the same as this. I simply replace eta with p. So let's do it very fast. So f equal integral 0 to L of p of x prime t delta x minus x prime in dx prime. With this observable, so we can we can redo the same calculations. So let me keep this expression here. So let's first compute df dt equal partial of f with respect to t plus the bracket between f and h. There is no extrinsic dependence on time, so this term is 0. Okay? So we need to work out this df dt. But df dt is pretty easy because is equal to integral between 0 and L of the p dt, which is computed at x prime t, times delta x minus x prime dx prime. So this is equal to the p dt computed at x. And now we can work out the we can work out the bracket, and f comma h is equal to the integral between 0 and L of the brackets of the commutator between f and h in delta x prime. But this commutator now involves the what? The partial of f with respect to eta times the variational derivative of h with respect to p. I get always confused. The partial of f with respect, the variational derivative of f with respect to p times the variational derivative of h with respect to q in dx prime. But now f doesn't depend upon eta. Okay, so this term is 0. I end up with this. The partial of f with respect to the variational derivative of f with respect to p is simply delta x minus x prime. Okay, and then this result is gonna be equal to minus integral 0L delta x prime minus x. The delta is symmetric, so I can always change x prime minus x on x minus x prime. Partial variational derivative of h with respect to q in dx prime, and this is going to be equal to minus the partial of h with respect to q computed at x. And that's where we prove that the pdx is equal to this. Okay, so we got d eta dt equal plus the variational derivative with respect to p, and now we also got these other results, the pdt equal minus partial of h with respect to q, with respect to, sorry, this is basically eta. And that's and our introduction to Hamiltonian system. Thank you.